Delta G standard and the equilibrium constant going to be the topic of this lesson. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, in addition to high school and college science prep, we also do MCAT, DAT, and OAT prep as well. I'll leave a link in the description where you can find those courses. Now, this lesson is part of my new general chemistry playlist. I'm releasing several lessons a week throughout the rest of this school year, so if you want to be notified every time I post a new one, subscribe to the channel, click the bell notification. So delta G standard and the equilibrium constant. Now, I really should talk about this in a little bit bigger context. So that is definitely going to be a big part of the lesson, but it's really delta G standard, the reaction quotient Q, and the equilibrium constant. This interplay among these four variables. And we're actually going to start with delta G standard versus non-standard, what the deal is here. And so the standard value is what we learned to calculate earlier in this chapter, like using free energy of formation values where you're doing like products minus reactants. That's how you get the standard value. Problem is that most of the time, and you're not under standard conditions when you're carrying out a chemical reaction. In fact, if you go to produce something in the lab, think about going into make a certain product in the lab. You're going to mix some reactants together and hope to make the product. Well, the initial conditions you start with, you have only reactants. You have no products. That is not standard conditions. So that circle again means standard conditions. And as a reminder, standard conditions implies that all your reactants, all your products have a concentration of 1. If they're aqueous species, they're all 1 molar concentrations. If they're gaseous species, all 1 atmosphere partial pressures. So notice it means you don't have just reactants, you have reactants and products, and they're all equal in concentration at a value of 1, either 1 molar or 1 atmosphere. So if you're going into the lab to make a certain product and you're starting with only reactants, that is not standard conditions. And delta G standard just doesn't apply. It is delta G non-standard that you really need. And so most of the time when you're doing a chemical reaction, you're under non-standard conditions, and this is how you calculate it. Now you start off by still looking up that standard value and calculating it from like free energy of formation values or something like that, and then you add on this fudge factor here that has the reaction quotient Q in it. And recall that the reaction quotient Q is products over reactants raised to the power of their coefficients, and the way it's different than an equilibrium constant is that those concentrations are measured. They don't have to necessarily be at equilibrium. And so what it's going to account for is that if any of those concentrations are not equal to 1, they're going to show up there. Now, however, if you look at, what's nice about this equation, the way it should be if it's a valid equation, is that if you are under standard conditions, well, then delta G should be the standard value. And so if you're under standard conditions and all reactants and all products are 1, well, then Q, products of reactants, are going to be a bunch of 1s over a bunch of 1s, and it's going to equal 1. And if Q equals 1, well, the natural log of 1 is 0, and this whole second term therefore goes away. And delta G just equals delta G standard as it should if you're under standard conditions. Okay, but what if you're not under standard conditions? What if all your reactants products are not equal to 1? Well, then you're going to get some value for Q, and delta G is not going to equal delta G standard. It's going to equal some other value. It might be higher, it might be lower, just depends on your conditions. So, but that's what this equation is used for, though, is to calculate what is delta G under some other set of conditions, and that's what we're going to look at in this first question. So that's the first question we're looking at. We're given this lovely reaction, N2 plus 3H2 giving 2 ammonia. We're given the standard delta G value at 298 Kelvin is negative 33.3 kilojoules. And then we're told the partial pressures of N2, H2, and NH3 here, and asked to calculate delta G non-standard, just plain old delta G, under these conditions at 298 Kelvin. Okay. Cool. First thing you're supposed to realize that you're not under standard conditions. These are not all equal to 1. So you're not under standard conditions. And if you're being asked to calculate delta G when you're not under standard conditions, that's the equation you use. And you need the standard value. That's why it had to be provided here. But that's just where you start. And then you got to add in this fudge factor here. And so that's what we're going to do here. So delta G equals the standard value. So negative 33.3 kilojoules plus RT, and you might recall R is your universal gas constant. When we're doing like PV equals nRT calculations, we typically use 0.0821 liter atmospheres per mole Kelvin, because we're usually using things like liters and atmospheres for pressure and volume. But when you're doing things in units of energy, especially in second semester Gen Chem here, most commonly you're going to have a second value of R provided that's in joules, SI unit for energy, and that's 8.314 joules per mole Kelvin. Now we got to be careful here, because if we just leave this alone, we're going to end up with a problem. So we're going to correct this in just a second. So, but temperature here is 298 Kelvin. And then we got ln of Q here. So, and if you look at this reaction here, we'll just kind of write this off to the side here, but Q is going to equal the partial pressure of ammonia squared all over the partial pressure of N2 all over the partial pressure of H2 cubed. So in this case, maybe we'll just calculate it out off to the side and just insert it in up there. So that's going to be 100 squared all over 0.1 times 0.1 cubed. Cool, and with nice powers of 10 here, you could probably do this in your head here. So 100 is 10 squared, and 10 squared squared is 10 to the fourth. Every time you divide by 0.1, that increases the power of 10 by 1. And so you're really dividing by 0.1 to the fourth. So you got 10 to the fourth over 10 to the, over 0.1 to the fourth, which is going to get you 10 to the eighth. So, but again, let your calculator do that as well. And so we're going to have ln of 10 to the eighth power, which is the same as 1 times 10 to the eighth power if you cared. Cool, and now we're ready to do some plugging and chugging if we make the units match. So if we're adding these two terms, they have to have the same units, either both joules or both kilojoules, or it's not going to work. So big common error here is not making your units work. Now, if this were a multiple choice question, then I would look at my answer choices and see, are they in joules or are they in kilojoules? If they're in joules, then by all means, I'd convert this to joules. If they're in kilojoules, well, then by all means, I'd convert R to kilojoules per mole Kelvin instead. Most likely, though, ΔGs are usually given in kilojoules, probably going to be reported in kilojoules. And so I'm going to convert my R here into kilojoules before doing the calculation. So instead of 8.314, I'm going to have to divide that by 1,000 to turn it into kilojoules. And that's going to be 0.008314 kilojoules per mole Kelvin now. And now we're ready to do some plugging and chugging in our calculator here. So we've got negative 33.3 plus 0.008314 times 298 times the natural log, and I'm going to put it in as natural log of 1 e to the 8th in my calculator, and we're going to get 12.3 kilojoules. So my question for you is this reaction spontaneous under these conditions? And hopefully you said no, because ΔG is positive under these conditions. My next question for you, though, is would this reaction be spontaneous under standard conditions? Well, yes, because ΔG standard is negative. And so under standard conditions, this reaction would be spontaneous. But we just determined by calculating out ΔG under these conditions that it is not spontaneous under these conditions. It's the reverse reaction that would actually be spontaneous under this given set of non-standard conditions. Okay, so that's the first thing we'll use this lovely equation for, is actually doing some plugging and chugging, calculate ΔG under non-standard conditions. So, but there's some relationships we can also take a look at as well of when a reaction might be spontaneous. So if you take a look, we know that, reaction is spontaneous when ΔG is negative. It's non-spontaneous, or the reverse reaction is spontaneous when ΔG is positive. And if the reaction has reached equilibrium, well, then ΔG equals 0. So as a reaction approaches equilibrium, what you're going to find is that ΔG, non-standard, is changing throughout the entire reaction, and it's getting closer and closer and closer to 0. And when it finally reaches 0, your reaction has reached equilibrium. Notice it is not ΔG standard that is necessarily going to equal 0 at equilibrium. It's going to equal whatever it equals when you looked up free energies of formation in a book. And those values in the book don't change. It's not like you calculate it, and then you run the reaction in the lab, and then you look up the values again in the book and somehow come out with a different calculation. This value is what it is based on the values you looked up in a book. It is the plain old non-standard ΔG that is changing all the time as the reaction proceeds. And again, once it reaches equilibrium, that's when it's going to equal 0. So common question is, which of the following is true about a reaction to equilibrium? ΔG equals 0. Yes, that is true. ΔG standard equals 0. Well, I mean, that might be true for certain really rare, unusual reactions, but it's not in general true for every reaction. It doesn't have to be true at all. It is just plain old ΔG that equals 0 for reaction at equilibrium. Now, if we look at that special case now of a reaction at equilibrium, well, for this to add up to a total of 0, that would imply that these two terms that we're adding together are equal in magnitude, but opposite in sign. One's positive, one's negative, but they have the exact same magnitude, and therefore add up to 0. And so at equilibrium here, these two terms add up to 0. And if you're at equilibrium, though, well, that's when the reaction quotient equals the equilibrium constant. And so the special value of Q that when you plug it in makes these two terms equal in magnitude, opposite in sign, that's when Q equals K. And we can rearrange this and come up with a nice lovely relationship. That's kind of where the title of this lesson comes from, that delta G standard equals negative RT ln of K. And for a given temperature, so, and again, keep in mind that temperature is the one thing that changes your equilibrium constant. It also changes the value of your standard delta G. You can have standard delta G at any temperature. So, but at a given temperature, if you know delta G, you can calculate K. If you know K, you can calculate delta G. And that's the second sort of calculation you might do. Now, before we get to that sort of calculation, because we will definitely do one, look at some other relationships though. So if Q equals K, well, that's when delta G is going to come out to 0. Well, we've got two other relationships we can kind of take a look at. What if Q is less than K? What if Q is greater than K? And before we look at them mathematically in the context of this equation, I'm just going to refresh your memory back with Le Chatelier's principle. When Q was less than K, we needed to make more products, and their equilibrium needed to shift to the right to get to equilibrium. And if the reaction needs to shift to the right to get to equilibrium, that means the forward reaction is spontaneous. So delta G would therefore have to be negative. Now, if Q is greater than K, we learned with Le Chatelier's principle, well, that's a reaction that needs to make more reactants, and the equilibrium needs to shift to the left. And that means that the forward reaction is not spontaneous, it's the reverse reaction that's spontaneous. The forward reaction is non-spontaneous, and delta G is now positive. We've reasoned that out from Le Chatelier's principle, but it turns out mathematically this is true too. At a very special value of Q, these two terms are going to add up to 0, and that special value is when Q equals K. But depending on if Q is a little bit bigger than that number or any smaller than that number, that's going to affect whether delta G comes out either negative or positive. Cool, totally in line with what we learned from Le Chatelier's principle. All right, one other thing we can take away here is a relationship between delta G standard and the equilibrium constant. So it turns out that if delta G standard is negative, and let's think about what that means for a second. So it means that under standard conditions, the reaction is spontaneous. Well, under standard conditions, it means that all reactant concentrations are 1, all product concentrations are 1, and they're all therefore equal to each other. Well, if the reaction is spontaneous in the forward direction under those conditions, then you're converting reactants into products on your way to equilibrium. And so your products are going to go up in concentration as your reactants go down in concentration. And when you finally reach equilibrium, you'll have more products than reactants. And if you have more products than reactants at equilibrium, well, that means that your equilibrium constant is bigger than 1. Now, what if delta G standard, on the other hand, is positive? Well, if delta G standard is positive, that means, again, under these standard conditions where all concentrations are 1, all the reactants, all the products, where they're all equal, well, now it's the reverse reaction that's spontaneous. The forward one's non-spontaneous. And so the reaction is going to go backwards, and you're going to make more products and make more reactants and use up your products. And so you're going to end up at equilibrium with more reactants than products. And if at equilibrium you have more reactants than products, well, that means that your equilibrium constant now is less than 1. And if on the odd chance you have one of those oh so rare reactions where delta G standard just happens to be really close to 0, well, that's when your equilibrium constant would equal 1. So, but again, not a lot of reactions. Most reactions you're going to have an equilibrium constant that's definitely not equal to 1 for most cases. So I just want to make sure you realize that equilibrium constants don't have to equal 1. All right, cool. So here's some relationships between Q and K and how that affects the non-standard delta G value. Here's a relationship between delta G standard and the equilibrium constant as well, and you should know both sets of these lovely relationships. Now, you might also be doing a plug-and-chug type calculation here as well. And if at a given temperature I give you K, then you can calculate delta G standard. If at a given temperature, again, I give you delta G standard, well, then you can calculate K. And the last one is the hardest one possible because solving for something under a natural log requires some math skills that are probably a little bit rusty because we hardly ever use them. But let's do that. Let's solve for something under that natural log because that's going to be the question we're going to answer here in a second. So first thing I'll do is divide by negative RT here. So we're going to have negative delta G standard over RT equals natural log of the equilibrium constant. And then we'll do, to get rid of that natural log, is e to the power of. E and natural log are inverse functions. They cancel. And over here, you got to do the same thing. So e to the negative delta G over RT And therefore, overall, you're going to get your equilibrium constant equal to e to the negative delta G standard over RT. So, and again, that's the equation we're going to ultimately use, just rearranging this one to look like this for this last question on page 74 here. So calculate the equilibrium, well, it might not be your page 74, this might change later on, but on this page of the handout. Calculate the equilibrium constant for the following reaction at 298 Kelvin. And again, this is going to be for the N2 plus 3H2 going to 2NH3 with the delta G standard being negative 33.3 kilojoules. Again, the same one we did for the last question. Same reaction anyways. And we want the equilibrium constant. Well, in this case, delta G standard is a big fat negative number. So at the very least, we should know that the equilibrium constant's greater than 1. And so if you got a multiple choice test, I mean, you don't have time to do the whole calculation, well, by all means, at least pick a k that's bigger than 1 based on what we established over here since delta G standard is negative. So, but we got to do some plugging and chugging and some calculations here. And we'll plug in some values. And again, one major thing again is units are important. Delta G standard and R either got to be both joules or both kilojoules so the units cancel out. So super important like we saw in the other calculation in this section here as well. So here we're going to have e to the negative, and again, don't forget that this is negative, but delta G standard is also given as negative 33.3 kilojoules. I'll just leave that in kilojoules. So R is 8.314 joules per mole Kelvin, and then temperature is given as 298 Kelvin for this problem. And once again, we have the same problem we had before where the units aren't going to cancel. Delta G's are usually provided in kilojoules. R is most commonly given, at least in terms of joules, as 8.314 joules per mole Kelvin. And whether I want to make this 0.008314 like we did in the last example, but in something like this, I usually find it easier to convert kilojoules to joules. So instead of negative 33.3, I'm going to multiply that by 1,000 and get negative 33,300 joules. Technically joules per mole, that way these units cancel, but same diff. And now the units are ready to cancel out there, and life is good. But if you'd made them both kilojoules, it would have worked out exactly the same way. And now we got some plugging and chugging to do. And most common mistake here is students forget that a negative times a negative makes it positive. They forget one of those negatives, so don't make that error if it's showing up in your problem. So in this case, we're going to have 33,300 divided by 8.314 times 298, all in parentheses. Cool, so I just calculated this part, and now I'm going to do e to the power of. And I already took into account, again, the negative times the negative. That's why I'm going to do e to the 13.440578 something, something, something. Just e to the last answer in my example. And that's going to give us 687,335.71116, which will round to, I don't know, 3 sig figs or so. And just say it's equal to 6.87 times 10 to the 5th. So 687,000, give or take. Cool, so we definitely see that K definitely ended up being larger than 1, as it should have, because delta G standard was definitely a negative number. Now that concludes the calculations for this section. We've got one last thing to look at, and that's some graphical relationships that come from these equations. So let's take a look at that. All right, so the plot we're going to look at has Gibbs free energy plotted on the y-axis, and it's going to look at the reaction progress as we go from pure A to pure B in this reaction, so pure A to pure B. And we're given that delta G standard here is going to be a negative number. And what that means is that we're going to go downhill in free energy, not uphill. And so what that ultimately means is that the energy of pure A is going to be higher than the energy of pure B. If delta G standard was positive, well, then that would be reversed. So, and it turns out we might think that, well, the reaction is just going to proceed along a straight line as we go from pure A to pure B, but it turns out that's not actually going to be true. So we got pure A to start with, we're going to end up with pure B to end with, but all along the way, we'll have converted some of the A into B, but we'll still have some A left, and we're going to have a mixture. So, and that has some profound implications, it turns out. So because you have a mixture, it lowers the energy. Now, it turns out that this is going to reach an energy minimum. So over here, closer to whichever one of these is lower in energy. And since B is lower in energy, then we're going to reach the energy minimum closer to having pure B than pure A. So if delta G standard had been a positive number, that would have again implied that this would be reversed and that A would have been lower, and then the energy minimum would have been way over towards the reactant instead of the product. But in this case, with ΔG standard being negative, that energy minimum is going to be much closer to being pure products than pure reactants. And we'll find out that's a reflection of the fact that the equilibrium constant's bigger than 1 when ΔG standard is negative. One of those lovely relationships we worked out a second ago. Now, a couple things on this graph. So first off, if we just kind of take a look at the difference in energy here between pure A and pure B, that actually gets you ΔG standard. So on this graph, if you had, a scale on this or a graduated scale of some sort, you could actually, approximate ΔG standard by just taking the difference between the energy, the free energy of pure B and the free energy of pure A, and noticing that it was negative going downhill. Now, why is the actual curve lower than this straight line that, truth be told, doesn't actually correspond to anything in reality? So, well, it turns out that as long as you're somewhere in the middle, you have A and B mixed together. And the key word here is mixed together. And so it turns out that when they mix together, you have this delta S of mixing term, this free energy of mixing. And if you recall, when you've got a mixture together, you have more possible microstates and therefore more entropy. And so, well, if you have pure A over here, there's no mixture. And if you have pure B over here, you have no mixture, and you're right on those points. But anywhere in between, you're going to be lower in free energy than this straight line because of the mixture, leading to greater number of microstates and greater entropy. And if delta S of mixing ends up being a positive number as a result of those more microstates, well, what that means, based on delta G equals delta H minus T delta S, that if delta S here is positive, so, well, negative T delta S, therefore, is going to come out negative, and it's going to make delta G more negative. And that's why this line, the actual energy line, as the reaction proceeds, is lower in energy. And it turns out that if you compare that straight line to anywhere of the actual line of free energy, that's where you get the delta G of mixing, between any 2 points on a vertical line. That would be the delta, corresponding to the delta G of mixing. And I've seen that come up a time or two on a question of what that corresponds to. Cool, and that would be any of these blue lines. All right, now this free energy minimum. So, well, it turns out as long as you're to the left of that free energy minimum, well, then this reaction wants to proceed to the right in the forward direction. If you're anywhere to the right, well, then to get lower in energy, lower in free energy, the reaction would want to proceed to the left. Well, it turns out the reaction wants to proceed to the right because that's when Q is less than K. The reaction wants to proceed to the left over here because that's when Q is greater than K. And that free energy minimum right there, that's where delta G is 0 because you can't go any lower. Delta G is negative in the forward direction here. It would be negative in the reverse direction, which means positive in the forward direction. So, but right at that point, that's where Q equals K. That means right at that point, at the free energy minimum, that's where you're at equilibrium. Cool, we can kind of see, some of the other relationships we determined, when Q is less than K, delta G was negative. When Q is greater than K, delta G was positive, and it was the reverse reaction that was spontaneous. And when Q equals K, that was when delta G equaled 0. And so all these lovely relationships we looked at mathematically, we're now kind of looking at more of a graphical presentation of them. And again, once again, had, instead of A going to B, had delta G standard been positive instead, well, then A would have been lower in energy than B, and the equilibrium would have lied much closer to the reactants than to the products because for delta G standard being positive, K is less than 1, and it's a reaction that favors the reactants, not the product. So just wanted to point that out. So this was kind of specific to this particular example. So, but these are the kind of things you should be familiar with. So you should be able to look at this and kind of ballpark delta G standard. If you got a scale on there, you should realize that anywhere left of equilibrium, so that Q is less than K, which means that delta G non-standard is a negative number. Anywhere to the right of equilibrium, so it's a reverse reaction that's spontaneous, but Q is greater than K, and delta G of the forward reaction is positive. And then right at that energy minimum, that's where Q equals K, and you are at equilibrium. Now, if you found this lesson helpful, then the like button as well as a comment let me know are pretty much the best things you can do to support the channel. And if you're looking for thermodynamics or Gen Chem in general practice, take a look at my General Chemistry Master Course. It includes over 1,200 practice questions, final exam rapid reviews, including practice final exams. I'll leave a link in the description. A free trial is available. Happy studying.